Arun sir, good evening sir.
Good evening, sir. ஆரம்பிக்கலாமா?
Yes sir.
Yes, sir. Okay.
Nilkant sir, good evening.
Good evening, sir. Am I visible, sir?
Yeah, visual sir.
Where is the video?
Pangrach, shall I start then?
Yes, sir. Sure.
Okay.
My video is not showing here. Am I visible, sir? Clearly?
Yes,
Yeah,
sir.
visible sir.
Yeah, you are visible, sir. You are visible.
Okay, sure.
Sendil sir, good evening.
Good evening, Chairman.
Good evening, sir. Good evening, sir.
Okay.
Yeah, good evening, Doctor. Good evening.
Good evening to everyone. It's my pleasure inviting you all for the weekly online lecture series webinar 60th, being organized by IEI Salem Local Center in commemoration of its 30th anniversary celebrations. I would like to invite the chairman IEI Salem Local Center to welcome everyone. Thangraj sir, please.
Yeah, thank you sir. First of all, wish you all a very happy new year.
Happy New Year.
Respected today's chief guest, Dr. Nilkant Das sir, our beloved honorary secretary, Dr. C. Damani ma'am, immediate past secretary Sendil Kumar sir, our Arumugam sir, esteemed members of IAS Local Center and also Tamil Nadu State Center, partnering institutions, organizing team, participants, students, Mr. Tiago and friends. A warm welcome and also good evening to each one of you present for this special lecture session organized by our IAS Local Center. First of all, I want to thank our organizing team led by the four engineers, Dr. Kumaril sir, Engineer Seldom sir, Dr. R. Satish Kumar sir and Arugam sir has diligently curated a year of events on this Engineers Talk webinar series. On behalf of IAS Local Center and on my own behalf, sorry, Arun sir, am I audible?
Yes, now audible, sir. Actually,
Yeah, thank you, sir. Actually, it give me immense pleasure to welcome our distinguished today's chief guest and keynote speaker, Dr. Nilkant Das sir, Assistant
Thank you, sir.
Professor,
Also for
School of
inviting me.
Computer Applications, KIT University, Bhubaneswar, Odisha. We are truly privileged to have you with us today, sir.
Thank you so much, sir, for inviting me.
Yeah, you are going to again sharing your expertise on the need for the day topic, dynamical investigation of the solitary solutions for the higher order nonlinear Schrodinger equations, arising in physical systems. Your vast knowledge and research accomplishments are an inspiration to all of us, and we look forward to an enlightening session, sir. I also extend a heartfelt welcome to all the esteemed participants, IA members, professionals, academicians, students, and our well-wishers who have joined us today through the virtual platform. All your presence adds immense value to this event and motivates us to continue our mission of promoting technical knowledge and engineering excellence. As all of us know, we already across the 30 year of anniversary of our IA SLC, and also we completed 60 webinars in this series to celebrate our 30th anniversary. Also, the today's session marks another milestone in our journey of knowledge dissemination and technical outreach. I request everyone to actively participate, engage with the speaker, and make this session truly memorable. Before I conclude, I would also like to express my sincere gratitude to Engineer Armo sir for the wonderful hosting, not only for this time, for the last 60 events. Let us come together and make this event a grand success. Wishing you all a productive session and a wonderful year ahead. Thank you. Jai Hind.
Thank you, sir. Now it's my pleasure and privilege to introduce our chief guest and keynote speaker, Dr. Nilkanta Das, Assistant Professor at the School of Computer Application, Kalinga Institute of Industrial Technology, University, Bhubaneswar, Odisha, India. Mr. Das completed his MSc in Mathematics in 2017 and his BSc in Mathematics in 2015. He has successfully qualified in several competitive exams, including the CSIR UGC NET, JRF, GATE, and Assam SLET. With 5 years of rigorous research experience, Dr. Das is a dedicated researcher with a strong focus on advancing applied mathematics, fractional calculus, mathematical physics, nonlinear dynamics, and mathematical photonics. He obtained his PhD in mathematics from the National Institute of Technology, Rourkela, supported by a prestigious Council of Scientific and Industrial Research CSIR Fellowship from the Government of India. His doctoral thesis, titled Numerous Novel Analytical Techniques for Solving Non-Linear Partial Differential Equations Arising in Physical Systems, reflects his significant contributions to the field. He has published 10 research papers in prestigious SCI indexed international journals and presented a conference paper at an IEEE conference. With these words of introduction, I would like to invite Dr. Nilkanta Das to present on the topic Dynamical Investigation of the Soliton Solutions for the Higher Order Nonlinear Schrodinger Equation Arising in Physical Systems. Over to Dr. Nilkanta Das. Sir,
Thank you.
please.
Thank you so much, sir, for inviting me in this wonderful session. And I'm very happy to be a part as a chief guest and keynote speaker of this wonderful session. And thank you. Again, thank you for inviting me. Thank you, sir. Should I share my screen, sir?
Yes, sir, please, sir.
Okay. Is it visible, ma'am, sir?
Yes, sir, visible, sir. Visible, sir.
Okay. So, okay, good evening again to all of you and respected sir and my dear friends. Today in the engineer's talk, I'm going to give on the title Dynamical Investigation of the Soliton Solution for the Higher Order Nonlinear Schrodinger Equation arising in Physical System. So, these are some contents. For example, what is the introduction, the nonlinear PD with the fractional effects, and how to find the exact Soliton solution for the time fractional resonant nonlinear Schrodinger equation, and the 1+1, that means space and time, dimensional resonant nonlinear Schrodinger equation with the dual power law nonlinearity. And another thing is that solitary waves and Soliton solution for the generalized 3+1 dimensional gross p-type-c equation with distributed coefficients and the 2+1 dimensional Melnikov equation. And the fourth one is the Soliton solution for the 2+1 dimensional cascade system governed by coupled nonlinear Schrodinger equation with a Carr law nonlinearity. And the fifth one is the Soliton solution of the fractional perturbed nonlinear Schrodinger equation and modified nonlinear Schrodinger equation with conformable fractional derivative. And the sixth one is the exact traveling wave solutions and Soliton solution of conformable M fractional modified nonlinear Schrodinger equation. And in the last, there is a conclusion of the task. So what is the importance of the fractional differential equation? Actually, fractional differential equation, that is the very interesting subject in the recent years, because that study in the variety of fields, for example, population genetics, chemistry, economics, biology, and various branches of engineering. Actually, the application of FDs, that means fractional differential equation, by using this, we can get an accurate and comprehensive representation for the inside physical phenomena and can get the new insights and prediction that we may not get by using the traditional integer order differential equation. And since it has lots of application in the several fields of nonlinear science, the investigation of the fractional calculus has one of the very interesting area of research in recently. And also the fractional calculus, that is the arbitrary order extension of differentiation and integration, and it has grown. We have seen that its popularity in last few decades. And obviously, what is Schrodinger equation? Schrodinger is a scientist, and he has established the equation IH del psi by del t equal to H psi, where psi is the IH del psi lambda psi. And in the Schrodinger equation, what is Schrodinger equation? Actually, Schrodinger equation is a partial differential equation. Here I am taking the non-linear. So I am taking, in case whenever I am taking the non-linear Schrodinger equation, obviously I am taking the non-linear partial differential equation. And that can be found in the various fields such as physics, chemistry, and engineering. And it has a lots of application in nonlinear models, also in the field of nonlinear science, uh, because it has a lots of application in the various research areas. And recently, the most active field is the investigation of traveling wave solutions and fractional effects because of various fractional derivative of different kind of models. So definitely the nonlinear partial differential equation and soliton, that are very important topics to analyze the nonlinear, what kind of wave I'm getting from the nonlinear model. And because it has a significant role in different kind of fields of natural sciences such as geophysics, biology, solid mechanics, optical fibers, and ocean engineering also. So what is soliton? Actually, soliton is one kind of solitary wave that behaves like a particle, and it keeps its amplitude, velocity, and shape whenever it's moving. So definitely finding the exact solution of nonlinear model, that is one of the most challenging tasks and sometimes maybe impossible in engineering, applied mathematics, and physics. And there are lots of analytical methods are available to find the exact solution for the nonlinear problem. For example, the modified auxiliary equation method, the predictor character split step Fourier method, and the complex amplitude answer scheme, and the improved tan phi j by 2 expansion. There are lots of application analytical methods are there. I uses some analytical method to find the solution of the nonlinear Schrodinger equation. So definitely these are some fractional derivative I have used in some of my research paper. For example, the modified Riemann level derivative that can be given by equation number 1. That is the definition. MRL is the modified Riemann level derivative. And there is another definition, that is the truncated M fractional derivative, that is given by equation number 2. And there is one more, that is the truncated Mitov-Lechler function, that is given by equation number 3. And there is one more conformable fractional derivative, that is given by equation number 4. And here the alpha is the order, fractional order, and obviously belongs to the open interval 0 and closed interval 1. And whenever alpha equal to 1, it's become the traditional integer order derivative. And whenever it lies between the open 0 and closed 1, it's become the fractional derivative. So our target is using the fractional derivative. So definitely we will take the values in between the 0 and 1. So some authors, they have investigated the higher order nonlinear problems. For example, the 2 plus 1 dimensional SK equation by using the Wronskian method. This is one method they have investigated in 2017. And 2019, Peng et al. Investigated the multi-solution solution for the 3-component couple nonlinear Schrodinger equation, and they have uses the Riemann-Hilbert method. And in 2019, there is a Bharma et al. They investigated the solitary wave solution for the 1 plus 2 dimensional nonlinear Schrodinger equation with dual parallel nonlinearity by applying the tan phi j by 2 expansion method. And in 2021, they investigated the resonant optical solutions by using the conformable time fractional nonlinear Schrodinger equation by the utilization of the extended rational sine cosine or sine hyperbolic cos hyperbolic and advanced expansion method. And in 2022, recently Young et al. Investigated the bifurcation and exact solution for the generalized DGH equation with cubic parallel nonlinearity. So what is the motivation of this work? So definitely, since I am working on the nonlinear Schrodinger equation, and it's nothing but a nonlinear partial differential equation, and I am using the fractional derivative. So it gives the understanding complex phenomena, what kind of nature of the nonlinear model can be seen by finding the solution. So definitely that is my target as a, can I find out the analytical solution? Because if I can find out the analytical solution, then for different kind of parameter values, we can investigate it one kind of nature, one kind of stability, and what kind of behavior I am getting from the governing model, I can investigate it. So understanding obviously complex phenomena and enhancing the predictive modeling. Obviously, whenever I get the analytical solution with the application of the fractional derivative, so we can predict what kind of behavior by changing the parameter values we can change, we can see in the model. And innovation and discoveries also is lots of scenario is there. So definitely the exploration of exact solution to nonlinear partial differential equation by using the fractional order derivative is definitely a primary motivate by the researcher to understand the model, predict, control, and to get the best solution of the complex model that has a lots of application in the several scientific and real world domains. So definitely there are several analytical methods that has been applied in different kind of model using the fractional derivative, because it has a influence of various factors and consideration. So here I have taken the time fractional resonant nonlinear Schrodinger equation. Here I have taken time fractional. Here I am taking the time as a fractional order and the space as an integer order. So that is given by equation number 5. That's why I d alpha t u. Alpha lies between open 0 close 1. If I put alpha equal to 1, then it's become the traditional resonant nonlinear Schrodinger equation. But to get the more flexibility and to get the behavior, understand the behavior of the solution, I have taken the time fraction. And what is U? U is the wave profile, complex wave profile, because at the imaginary part is there. So definitely that is a complex function. And obviously this is a complex equation. And here alpha and alpha 2 and alpha 3 as the parameter. They have some alpha 1 known is the coefficient of group velocity dispersion. And alpha 2 that is known as the non-Kerr nonlinearity. And alpha 3 is known as the coefficient of resonant nonlinearity. Now, how to use the modified auxiliary equation method to the time fractional resonant nonlinear Schrodinger equation. That is our model. So how to use? Because this is the modified auxiliary equation method. That is the analytical method. So there are some procedure. First procedure is, suppose the nonlinear partial differential equation is given. That is given by equation number 6. And here the modified Riemann level, there are lots of derivative. For example, conformable fractional derivative and the m fractional conformal derivative. Here I have used the modified Riemann level derivative, and different derivative has a different advantage for the model. So here d alpha tu is the modified Riemann level derivative for the wave function u. So definitely whenever we are taking the nonlinear model, it's generally the nonlinear partial differential equation, and directly solving the nonlinear partial differential equation is very challenging and it may not be possible. So our task is how to transfer, how to convert the nonlinear PD to nonlinear OD, because whenever we can transform the nonlinear PD to nonlinear OD, then we can easily apply some kind of method and we can find out the solution. And here I have used the wave transformation that is given by uxt equal to u zeta, and zeta is xi equal to u xi equal to is the linear combination of x and t with the constant k and c, kx plus ct. So here I have used this wave transformation in the governing model. That means whatever the nonlinear PD is given. Then after using the wave transformation, then it's easily converted to the nonlinear OD. And whenever we got the nonlinear OD, then we can find out the solution by using the method. And here the method name is modified auxiliary equation method. And for the procedure to apply this method is assume the solution of the nonlinear OD in this form. That is given by equation number 8. And here m is the parameter. That means the value of the m should be integer. So definitely there is a function in equation 8. There is a function fj, and how to find the value of fj we can find out from the equation number 9. These are the procedure of the modified auxiliary equation method. So we can find out the value of fj by solving f dash j equal to this one, and that is given by equation number 9. And obviously there is a Kerr law nonlinearity. Kerr law is one kind of, suppose f psi equal to psi. So definitely whenever I am using the Kerr law, because in equation 5, f mod of psi square, f mod of u square. Whenever we use, then Carlo, if we use Carlo, f mod of u square is u square. F psi equal to psi. That is the property of the Carlo nonlinearity. So definitely, after using the wave transformation, I got the equation number 10, and this is the in this form. So then, what is the procedure? I have to use the wave transformation. So here, since this is the complex equation, so I have taken the exponential part, u xt equal to u j. If it's become the real equation, if no imaginary part is not present, then we can take the uj. Hence, since the iota is here present, and that's why I have taken uj exp I theta. And obviously, xi is the linear combination of k and c, and theta is also linear combination of x and t. So whenever we use the wave transformation in the equation 10, that means in the model, so we find out the nonlinear ODE. And since it is a complex equation, so there will be, whenever we equate the real part and imaginary part, because two equation I will get by equating the real part and imaginary part. So I obtain the equation number 12 by equating the real part, and I got C is the velocity of the wave, and here the soliton. So definitely, I got the velocity value of the soliton speed C equal to minus 2 L alpha 1, and that has been obtained from the imaginary part. So after then, I have applied the homogeneous balance principle. And whenever, what is homogeneous balance principle? That means in nonlinear OD, I am taking the highest order derivative, equating the highest order derivative and highest order nonlinear term. And using that, I got the m equal to 1. So definitely, whenever I got the m equal to 1, we got the solution form uj equal to in this form. So whenever we substitute this in the governing model, that means nonlinear OD, we got this kind of solution, because beta square minus 4, if this condition, for this condition, I got equation number 14 and 15 kind of solution. And for beta equal to 0 and eta equal to sigma, I got equation number 16, that is another kind of solution. And whenever, and this is the graphical representation, because here I have used the modified Riemann level derivative, and alpha is the order of the modified Riemann level derivative. So here I have taken alpha equal to 0.99. If I take the 1, then definitely it's become the traditional. So I have taken the alpha equal to 0.99, and I have seen that it's given the solitary wave, and I have taken the absolute of u1 xt, and that is available in the equation number 14. So definitely, and there is another graphical representation of the obtained solution. That is, this is the bell-shaped soliton solution for the absolute of u3 xt, and these are some parameter values. For this specific parameter values, I got this graphical representation. If I changes the parameter values, then I may get the different kind of graphical representation. But for this particular specific parameter values, I got this graphical representation. That is the bell-shaped soliton solution. And in the same way, I have utilized the 1 plus 1 dimensional resonant nonlinear Schrodinger equation. Dual power law. Why dual power? Because in the equation 17, there is a double power. One is the B mod of u square and C mod of u2. Power is two powers are present. That is the reason the equation name is dual power law nonlinearity is there. And definitely, this is also the complex equation. Like the previous model, and this has been solved. Here I have changes the methodology, that is the Kudryashov. In the previous model, I have applied the modified auxiliary equation method, but here I have applied the Kudryashov R function method. And in the same way, same technique, whenever I use, and the methodology is different, because this analytical technique, and every analytical technique has the advantage, more advantage as comparison to maybe the previous advantage. So I have uses the Kudryashov R function method, and this is the procedure is here. The assumption of the equation number 21 is in this form. So definitely here logistic function has been present in this model. That's 1 by C1 exponential gamma j plus D1 exp minus gamma j, and C1 D1 gamma parameters. So here the logistic function Rj that can be obtained by solving the differential equation that is given by equation number 23, and capital J equal to 4C on D1. That is the condition. So definitely, in the same way, I assume the traveling wave transformation like the previous model. I have assumed in this form. bar theta equal to in the form of in the linear combination of x and t, and in the same way xi also x and t. So definitely by solving again, but here whenever I use the homogeneous balance principle, for example, by equating the real and imaginary part, I got equation number 25 from the imaginary part, and I got the real part from the real part I got the equation number 26. Now in the real part I use the homogeneous balance principle between the highest order derivative. Highest order derivative is u5, and highest order nonlinear term is u double dash. Okay. So definitely, whenever I use the homogeneous balance principle, I got m equal to half. But my target is the value of m should be integer. So in that case, I use the transformation, and whatever you get the value of, you take the transformation u equal to b to the power that value. That means b to the power half. And whenever you again put in the equation number 26, I got the equation number 27. Again, I am applying because my target is to find the integer order value of the for the m. So definitely, whenever again I utilize the homogeneous balance principle, again I got m equal to 1. So definitely, since it's the Kudryashov R function, Kudryashov is a scientist, is a dedicated researcher, and he has proposed this method. That's why Kudryashov R function method. And logistic function is presented. That's why R function. That is called the R function method. So definitely, whenever m equal to 1, I got. So definitely, whenever I put this in this equation, that means in this form, in this assumption, I got Vj equal to B naught plus B1 Rj. So I got this, and again, see in the same way, put this to the equation number 27, and after solving this and we'll get the system of nonlinear algebraic equation, and after solving all the algebraic equation for the different kind of parameter values, we got suppose there will be lots of parameter conditions will be there. So whenever we use these values, and we use the logistic function Rj in this form, so I get a equation 30 that is given. That is one kind of traveling wave transformation, traveling wave solution, a wave solution. And there is another condition. Whenever d1 equal to c1, I got the hyperbolic solution, sec hyperbolic, that is the bright solution. And whenever d1 equal to minus c1, because two possibilities are there, either d1 equal to c1, either d1 equal to minus c1. Whenever d1 equal to c1, sec hyperbolic, and whenever d1 equal to minus 1, I am getting the cosec hyperbolic. That means singular solution I am getting. And this is a bright solution. That is the equation number 31. Just that is the sec hyperbolic. That is the 3D bright solution surface. That means what kind of graphical representation I can get from the obtained solution for the governing model. So I have shown and there is a contour graph of U1 on xt and occurring in equation 31. So definitely there are another method. There are 4 or 5 methods I have applied in the different kind of nonlinear models. What kind of solution I can get in my research paper. So there is a generalized Kudryashov R function method. There, the assumption of the solution is in the form of equation number 33, and sigma I and tau j. Their ranges is 0 to n and 0 to m. They are real valued constants. And the function here, the q j is the function that is by 1 plus rho e to the power j. And what is rho? Rho is the integral constant. And how to find the q j? That can be obtained from the equation number 35 by solving the q dash j equal to q square j minus q j. And for the remaining steps, we can see the reference number 35. And again, you use the homogeneous balance principle, and we get n equal to m plus 1. So I got the n equal to m plus 1. So I can take m equal to 2. For m equal to 2, n equal to 3 will be there. So for the flexibility and to get the easily, so that we can get the easily solve the problem, we have taken the m equal to 1. I can take m equal to 2 also. For m equal to 2, I will get the different kind of solution. Here I have taken m equal to 1. In my research also I have taken m equal to 1. Somebody may take for further research, they can take m equal to 2, 3, 4, 5, etc., etc. So for m equal to 1, n equal to 2. And whenever in equation 33, there is n in the numerator. In numerator, there is n, and in the denominator, there is m. So definitely, whenever we put n equal to 2 and m equal to 1, we got this form that is given by equation number 36. And whenever again we put this value of Vj to the nonlinear OD, we get some kind of parameter values. And whenever we getting the some kind of parameter values, again we put in our model, and definitely we get the solution that is given by equation number 38. This is the 10 hyperbolic function. And this is the King-Soliton solution. And there is the contour graph of the absolute of uxt, wxt. And that is given by equation number 30. What kind of, and there are some parameter values. I have skipped, I have not shown in the parameter values, but there are some specific parameter values. I got the King-Soliton solution for the equation number 38. And there is a generalized 3 plus 1 dimensional gross p type C equation with distributed coefficient. So here I have taken, that is given by equation number 39. And obviously, since it is a complex equation, so obviously like the previous assumption, I have taken u equal to u exp ib. And here u is the, obviously u is known as the amplitude, and the complex function u in terms of amplitude and phase. That means we have represent the u in terms of amplitude and phase. That is, amplitude is u and phase is in the form of b. So we have present the complex function u in the terms of amplitude and phase, that is given by equation number 40. And again, whenever we put this in the in our model, we get the since a complex equation, so real part, imaginary part will be there. And from the real part, couple equation, this is a couple equation. I got couple equation for u and b are determined by putting equation 40 into equation 39, which are given as this. So here I have utilized the extended Jacobi elliptic function expansion technique, and we assume the traveling wave solution for equation 41 and 42 in the following form. That means given by 43, 44, and 45. And whenever we put, we get this kind of solution that is given by equation number 46, and where m represents the modulus of Jacobi elliptic function, and zeta is the, that is given by equation number 47. And this is the graphical representation of the model of the solution, obtained solution, equation number 46 in the 3 dimension. This is the 3 plus 1. That means 1 means time and 3 means space. That means 3 means x, y, z, and 1 means time. So x, y, z, t in the form. That's why 3 plus 1 dimension. So that is the 3D periodic, because the wave are again it's coming into the same position. So 3D periodic singular solution, and for the specific parameter values that's given in the figure. And there is one case there, since this is, I have applied the extended Jacobi elliptic function method. So whenever m goes to 1, I get this kind of solution that is given by equation number 48. And whenever m goes to 0, I got another kind of solution that is given by equation number 49. So definitely this is another model, 2 plus 1 dimensional Melnikov equation. So here the solution, I have applied the Kudryashov R function method in the previous in our model. I have applied. This is the couple equation. That is the Schrodinger equation. This is the 2 plus 1 dimensional Melnikov equation. This is another model. So here I have assumed the wave transformation. I have assumed solution of 50 by using the Kudryashov R function method. I have assumed in the form of equation number 52, and the zeta and theta is in the linear combination of x, y, and time t, and in the same theta was also in the linear combination of x, y, and t. And whenever in the same way, equating the real and imaginary part, we get the equation number 54 and 55. And whenever we put, and I got the equation number 56. And again, since it's getting the difficulty, we can integrate, and taking the integral constant to 0, I can get the equation number 57. And whenever now I can use the homogeneous balance principle to find the value for the m. So that is given, and after finding all the parameter by using the homogeneous balance principle and the solving the system of nonlinear algebraic equation, I get this kind of solution. And there is same in the Kudryashov method. There is same model procedure. Whenever b equal to a, I get the hyperbolic solution, and whenever b equal to minus a, I got the another kind of whenever b equal to minus a, I got this. And this is the graphical representation. This is the W-shaped Soliton solution. And this is the 2D representation for the time t equal to 0. Some parameter also present. I have not shown. Only time for the value of the time is given. The 2D graph, and there is a contour graph of absolute of ut1 txy. That's appear in equation number 60. And this is one more model. That is the 2 plus 1 dimensional Kaskagat system that's governed by couple nonlinear Schrodinger equation with Carnot nonlinearity. So also again, I applied the Kudryashov R function method, and I have utilized the equation number 66, and again the linear combination of eta, theta, and the j varies from 1 and 2. That means there will be some kind of changes in J. So definitely I will get the 68 and 69, and there will be another equation number 70 and 71. Here from the 70 and 71, since to find the velocity of the soliton, C is the speed velocity of the soliton. So 70 and 71, I equate them. I find out the value of C from both 70 to 70, and I equate, since the speed should be equal. So I equate 72 and 73, and I got one kind of expression that is given by equation number 74. And again, the homogeneous balance principle and using the Kudryashov R function method, I obtain the solution for the equation 68 and 69, and that is in the form of 75 and 76. So definitely by putting this 75 and 76, and by using the Kudryashov R function method, I can find out the system of nonlinear algebraic equation. And after solving the system of nonlinear algebraic equation for the specific parameter values, I can find out this solution that is given by equation number 77 and 70. Since this is the couple equation, so UV is there, 77 and 78. And these are the representation, U1, 1, UI1, XYT. These are representation to denote to change, to see the changes of the obtained solution. And again, in the whenever b equal to then we get equation number 79 that is given, and that means hyperbolic. Whenever b equal to I will get the hyperbolic solution, and that's in kind of sec hyperbolic, and that is a bright solution. And this is a 3D bright solution of the equation 64 and 65 of equation that's appear in 79, and these are some specific parameter values to draw this graph, because it's represent the behavior of the obtained solution for the governing model. And whenever b equal to minus a, then equation 77 and 78, I got equation number 81 and 82, and we can see the model. This is the cosec. This is a singular soliton solution. And there is a space-time fractional part of nonlinear Schrodinger equation. Why space-time? This is the here in this model. I have taken the time fractional as well as space. That's why space-time fractional. That is the reason. So alpha denote the time fractional, beta denotes the space fractional. So whenever to get the flexibility and for the simplicity, I have taken n equal to 1 and use the Carlo. What is Carlo? Carlo, the if function of psi equal to will be psi. And whenever I use this n equal to 1 and Carlo nonlinearity in equation number 83, I got the equation number 84. And in the same way, I take the fractional complex transform, like the wave transformation. I have taken this amplitude and phase form, and chi and theta is there. And now, whenever we put this fractional complex transform into the equation that is given by equation 85 into the equation number 84, I got the two equation and one equation is from the real part and one equation from the imaginary part. And one equation from the real part, I got the equation number 86, and from the imaginary part, I got the C equal to C is the velocity of the soliton, sigma k minus 2 kl, and I got the another parameter values, that is the lambda equal to minus 2 by 3 gamma. That will be useful in the graphical representation. So I use the homogeneous balance principle, and I use the improved 10 phi j to here. This is also this method has a significant role for finding the analytical solution of the nonlinear model with the fractional effects, improved 10 phi j to expansion method. The traveling wave solution that is given by equation number 87. And for the simplicity, I have taken the p equal to 0. So whenever p equal to 0, 87 becomes the 88. And by considering the equation 88, equation 86, and I use the improved 10 phi j to expansion method, I will get a system of algebraic equation. And I again will solve the system of algebraic equation with the specific parameter to get with the specific parameter values, and I got the psi tx that is given by equation number 89. And this is the graphical, this is a 3D kink soliton solution surface of the absolute of psi tx, and here the space time fractional is taken as the 0.79, and the space fractional value has been taken as the 0.89. That's why this is the fractional. And what is the theta and xi? Theta and xi is the linear combination of this is the fractional form. So obviously there is a modified nonlinear Schrodinger equation with the conform. Here in the previous model, I have applied the modified Riemann level derivative. Here I have applied the conformable fraction derivative. Every fraction derivative has a lots of significance in the model. So here the modified non-linear Schrodinger equation with the conformal fraction derivative that is given by equation number 90, and here the q star is qx star. This is a conjugate, complex conjugate. For solving the equation 90 by using the Kudryashov R function method, I have assumed the wave transformation that is given by equation number 91, and we substitute in the same like the previous work. I substitute the equation number 91 into 90, and I separate the real and imaginary parts. Again, I got the equation number 92 that is obtained from the real part, and 93 is obtained from the imaginary part. Okay, now I integrate equation 93 with respect to with respect to zeta, and I am taking the integral constant equal to 0 for the simplicity of the model, and that gives the equation number 94. And from equation 92 and 94, see, from equation 92 and 94, I got the equation number 95. And from 95, I got some, by equating them, I got the velocity of the soliton and the parameter value L. And again, I use the homogeneous balance principle and Kudryashov R function method. The solution of obviously 92 will be in the form that is given by equation number 96. And whenever we substitute this and solving the system of nonlinear algebraic equation, I got this kind of solution that is given by equation number 97. And again, for B1 equal to A1, I got the sec hyperbolic, that is the bright. That's why this is a bright soliton solution surface, and B is the 2D solution graph at the value t equal to 0, and there is a contour graph of absolute of Btx appearing in equation 98. And for B1 equal to -1, I will get the singular soliton solution. That is the cosec hyperbolic that is given by equation number 99. And in the same way, I got another family of solution that is given by 100, equation number 100. And for B1 equal to 1, I got the this, and for B1 equal to -1, I got this kind of, that is the again in the hyperbolic solution, but this is the singular. And obviously, this is the bell-shaped bright soliton solution, and one is the 2D solution graph at the parameter value at the value t equal to 0, 1, and the contour graph for the absolute of Vtx that's appearing in equation number 101. And lastly, this is the modified nonlinear Schrodinger equation with truncated M fraction derivative. In the previous, I have applied the modified Riemann level derivative, then conformal fractional derivative. In this model, I have applied the truncated M fractional conformal derivative. And here also the conjugate complex is there. QXT is the complex function that represents the slowly varying container of the carrier Rogu waves in ocean engineering. And these are R1, R2, R3, R4. All the models have the lots of application in the ocean engineering and real life problems, and also in quantum mechanics, electromagnetic signal processing. That's the reason. Schrodinger. That's why Schrodinger equation has a lots of applications. That is the reason I am investigating the solution of the Schrodinger model, because analytically very difficult to find out the analytical solution. And sometimes it may not be possible to find some kind of model we may not get the analytical. So in that case, we will use the numerical method. So omega naught, that is a frequency and can denote the wave number of the carrier wave. So that is again in the same way I have truncated M fraction derivative with the nonlinear PT that is given by equation number 104. And in the same way, like the previous work, I have assumed the traveling wave transformation that is given by equation number 105. And whenever I use the equation number 105, the nonlinear OD can be transformed, the nonlinear PT can be transformed to nonlinear OD. That in that PT, the fractional form is there, but in that fractional form, I have transformed the nonlinear OD that is given by equation number 106. And since I have applied the modified, here I have applied one methodology, and that methodology gives the, whenever there is a type, some kind of condition. Type 1 is that u zeta equal to will be in this form that is given by equation number 107, and there will be some system of equation. There is a system equation omega zeta and delta zeta that is given. We can find out the omega zeta and delta zeta by solving the equation number 108. That is the couple equation. And where what is the delta square zeta? Delta square zeta is given by equation number 109, and here epsilon equal to plus minus 1. And obviously here the rho and lambda should be non-zero and sigma equal to plus minus 1. And whenever lambda rho becomes 0, then in that case the solution become like the equation that is given by equation number 110. And in that case, the delta zeta satisfies the equation number 111. And for there are lots of steps are there. I have skipped, and one may see the reference 47. So, and again, the complex traveling wave transformation that is given by equation number 112. And whenever we use the complex wave transformation and we put in the nonlinear OD, and we equate the real and imaginary parts, we can find out some kind of solution, some kind of equation. And from the imaginary part, I got 113 equation, and from the real part, I got the 114. And whenever I integrate equation number 113, and I take the integral constant as a 0. So in that case, I get the equation number 115. So from equation 114 and 115, I got the condition, some kind of condition that is given by equation number 116. And whenever I equate that in equation 116, I get some parameter values, that's given the delta and delta 1. And again, my target is to find the value of m. That's why I have again applied the homogeneous balance principle. And definitely I got the solution for the nonlinear OD that is given by equation number 19. And here one thing is that H1 or F1 should be non-zero. Both should not be zero at a time. One should be non-zero. In that case, the methodology is valid, otherwise invalid. So since here is the epsilon is given, epsilon equal to plus minus 1. Here I have taken minus 1 for the complexity. So whenever I take the epsilon equal to minus 1 and we substitute equation number 109, and again I utilize the equation 108 and 109 in the equation number 1 and 4, I got some kind of values that is given by equation number 120. And for this specific condition, epsilon equal to minus 1, sigma equal to minus 1, and rho should be greater than 0. In that case, I got the solution of the model by using the generalized projective Riccati equation. Here I have applied the GPREM, generalized projective Riccati equation. This is another new scheme, and I got this solution for the governing model using the truncated m fractional conformable derivative. And there is another condition for the whenever sigma equal to 1 and sigma equal to minus 1, I got another solution that is given by equation number 1 to 2. And this is the graphical representation. This is the 3D king-shaped Soliton solution surface. And another one is the contour plot. And last one is the density plot of the absolute of Q2xt. That's appeared in equation number 122. And that was the set 1 solution. The lot of set of solution I got, and that is the set 1. And in set 2, this condition is I got. And for this specific condition, I got the solution of the model by using the GPREM, that is equation number 124. And for case 2, for this specific condition, I got equation number 125. And this is the graphical representation. This is the 3D dark soliton type traveling wave solution surface. And there is the contour plot and density plot of the absolute of Qxt. That's appear in equation number 124. So in conclusion, what can I say? In this study, I have applied lots of analytical method to the different kind of nonlinear higher order Schrodinger equation. That means higher order nonlinear models with the fractional effects. Integer I have not taken. Here I have for the to understand the behavior of the to understand the accurate behavior of the governing model, I have applied several kind of analytical technique and to understand the behavior. So several kind of exact soliton and solitary wave that has been obtained in this study by using the different kind of approaches. And definitely I expect that these results will be highly beneficial and physical application of nonlinear optics and quantum mechanics, because they study the wave. So definitely this solution has a lots of significant role in the quantum mechanics and nonlinear optics, and also in different kind of science and engineering field. So definitely this work will be greatly help in acquiring the more in-depth understanding of the optical solution. And these results also allow the researcher to gain the greater insight into the optical theory. And there is a graphical representation. I have shown the graphical what kind of for some specific parameter values, what kind of behavior I am getting for the governing model for the specific parameter values. So graphical representation and physical validation of the several investigated obtained solution are described using the different kind of contour plot, density plot, and 3D plot and 2D plot I have shown in my work. Also, that's available in my research paper. And lastly, my obtained solution show that all the applied whatever all the methods applied are precise, and they are very efficient and effective, and very useful for the nonlinear model. So in future, what can I say? In future, many researcher can investigate it, the identification of novel classes of nonlinear PD that yet to be studied to find the exact solution. Because finding the exact solution, whenever we get the exact solution, we can find the behavior of the model, and we can investigate the stability analysis. And in one of my paper, the stability analysis also studied. And it would be beneficial to explore the potential application of existing technique. Some techniques has been utilized. We can utilize this technique to the novel nonlinear PD with the fractional effects that explore the equation, and thereby expanding the range of equation that may be solved. So also one may analyze what kind of behavior of the obtained solution for in different asymptotic regimes, and they can investigate their stability feature. Obviously, since nonlinear Schrodinger equation, that means the nonlinear system that exhibit the chaotic behavior and instabilities, and also investigating the chaotic solution and their implication, also developing the methods to control the chaos may be a very interesting and attractive area for the researcher in the recent field. And this paper, this work has been published in this journal, some kind of journals, and also all the works already published in some reputed journal, SCA journal. And this is a conference paper that has been that is the International Conference of Fractional Difference and Application, that is in Dubai, United Arab Emirates. That has been published in IEEE Explore. And these are my some references, whatever I have taken in this topic to explore and to understand and to investigate the governing model. So these are some references. And okay, thank you. Thank you.
Okay. Thank you very much, sir, for your wonderful presentation. Now I would like to invite the Honorary Secretary, IEI Salem Local Center, to propose a word of thanks.
Thank you, sir. Audible, Dunning, sir?
Thank you
yes,
so much, ma'am.
Yes, sir. First of all, wishing you all a very happy and a prosperous new year, 2025. Our
Yes,
most
Happy New Year.
respected, thank you, sir. Our most respected chief guest and
Thank you so much, ma'am, for inviting in this wonderful session. I'm very happy to be a part of this session. And Happy New Year to you. Wish you all the best for the upcoming time for this year.
thank you, sir. Thank you. Our keynote speaker, Dr. Neelkanda Das, sir, beloved chairman, Dr. K. Tangaraj, sir, respected committee members, council members, respected immediate past Honorary Secretary Sandil Kumar, sir, Mr. Arumugam, sir, Mr. Thiago. Good evening to all. It's my privilege and honor to propose vote of thanks on this great occasion of 30th anniversary, a special online lecture as a part of engineers talk. This is 60th lecture in the lecture series. The topic is dynamical investigation of the Soliton solutions for the higher order nonlinear Schrodinger equations arising in physical systems. On behalf of IEA Salem Local Center, I would like to express my heartfelt gratitude to our chief guest and keynote speaker, Dr. Neelkanda Das, sir, Assistant Professor, School of Computer Applications, KIIT University, Bhubaneswar, Odisha, for his excellent presentation. I sincerely thank our distinguished speaker for his insightful presentation, which deepened our understanding of this complex, fascinating topic. Thanks for accepting our invitation and gracing the occasion with your warm presence, sir. Thank you. Thank you so much, sir.
Thank you so much, ma'am, for inviting in this wonderful session.
My sincere My sincere thanks to our beloved chairman, sir, Dr. K. Tangaraj, sir, for his dedication and meticulous planning for creating a platform for learning and collaboration. Thank you, sir. I would like to convey my special thanks to our immediate past honorary secretary for his valuable presence and great motivation. I extend my special thanks to our engineer stock team members, Dr. R. Satish Kumar, sir, Dr. A. Kumarvel, sir, Dr. Engineer N. Armugam, sir, Engineer K. S. Selvam, sir, for their support always. I would like to thank Engineer N. Armugam, sir, for his unwavering support. Thank you, sir. I would like to express my appreciation to Mr. Tiago for his cordial support and organizing this webinar successfully. Thank you to all the participants for your enthusiasm and active involvement in this new year. Your presence and engagement made this seminar insightful and successful. We truly appreciate your contribution. I would like to express my sincere thanks to you all